networks they were running as they were advancing on that. The front one would be worrying about front lines, the back one worried about when the pieces got in, and they would roll them. They would take the back one, they would disassemble it and then move it to the front, refigure with new software and everything, and they would leapfrog like this. All networks works as they went along. It was really tough. It was one of the limiting factors in terms of making the whole thing work. And there are a lot of places where it's even harder. So I'm going to show you where we are now and talk about it a little bit. Question, what's the most complex thing in the home? I'm afraid I don't have a remote control, so I'm probably going to stand in your way. It's clearly, when I was a kid, it used to be the television set. Well, the television set doesn't even show up anymore in terms of complexity. It's clearly a computer and your internet connection. And if you ask what the most complex thing in the office is, it's clearly a network. Now, you're all used to networking, and there are a few people in the room who actually know how to make networks work, although I've watched the dynamics around here. When it doesn't work, you go ask Yvonne. Yeah, right, everybody laughs, so you understand the problem. Okay, and the problem is we've only got one of him. Put them together in a typical home or small business, and what do you get? Move this over to the side, because it really doesn't have to interfere with you. In fact, let's sit over here. Yeah, okay. I can do this without standing in front of anybody. Okay, you get a mess, and you get a lot of unhappy people. My colleague, Michael Littman, over in Hill, is now keeping a log of all the people's homes he visits and tries to hook his wireless computer up to. He's running about a 50% hit rate. And he has two choices. Either it connects and works pretty soon, or he can never get it to work at all in the sort of 2-day stay he has at somebody's house. We're running about 50-50. Okay, if you're going to deal with home networking today, what do you have? It's PC-based, which is already a problem. It's general purpose. The lower protocol layers are exposed, and I'll show you some good examples of that. I mean, they're exposed to people who can't spell protocol. It's designed for the office environment, which means lots of good support, more than one person like Yvonne around. Difficult instructions and customer support. Multi-vendor, multi-operating system, multi-application, etc. at home. You have a brand new 5 gigahertz Pentium in the kids' room, and then you do your business work on this 250 megahertz Pentium 1 over here, and you've got all kinds of stuff. But the most important part is there's no single point of responsibility for performance in people's home. Nobody's responsible except maybe the teenager. It depends on whether you can find him when you need it, or her, as the case may be. Okay, what would you like to do? You'd like to turn networking to a stage 3 technology. Just to put it into perspective, a stage 1 technology is for geeks only. Example, cars in 1910, right, or networks in 1980. A stage 2 technology. It's popular, necessary, but extensive user knowledge is needed. Example would be a car in 1950 where you're always fiddling around to keep it running, but you had to have one, or networks now. What you'd like to have is a stage 3 technology, something that's invisible where you focus on the results. And an example would be a soccer mobile today. You guys are all too young to be in that part of the world, but when you get to be sort of middle-aged, you've got kids, your car is something that gets them to a soccer game, and you really don't care how it works or want to know anything about it, except you have to tune it up every 100,000 miles or replace it. Data networks that function like the phone network. You pick up a phone, and you used to be able to just make it work. Let me show you an example of what it looks like in the outside world. This is Netgear, one of the companies that makes consumer home Wi-Fi networks. Easy install access point. This is right out of their instruction manual. Open the box and verify the contents. Connect the access point to the PC with its USB cable. Install the access point USB utility. Modify the wireless settings. Enjoy being connected. Your time, 10 minutes. Okay, that's like the same 10 minutes on the U.S. tax forms. And it's just as reliable. Okay? Let me give you an example. On that access point, here is part 4, modify the wireless settings. This is the text behind it in the appendix. Just take these 14 things, which are ESSID, rep disable, fragmentation threshold, which needs to be a number like 2346, RTS threshold. Just click on each of the 16 parameters to modify, which is what it says down here, and click OK and you're done. Right? How many people do you think on the planet can do that outside of this room or inside this room?
Rich?
Yes?
If one clicks on default settings, would it break it?
No, usually not. And it almost never works the first time. The other thing you didn't see, and nobody said it, nobody answered the question because I'm talking too fast, but on the easy four-step thing, there was one important little detail missing. It didn't say to plug it into the network card. So no matter what you did here, it wouldn't work. It actually didn't. It shows a picture of a Cat5 cable, but it doesn't actually say to plug that into anything, like into the box. If you didn't know what that cable was, you didn't have a chance. Okay. Most users want their tools to work, not be a challenge. Computers are getting to this point, sort of. You've seen the ads for Macintosh that say, I always used to think it was my fault that it doesn't work. Right? But networks are far, far away. There are many technical solutions, very few non-technical ones. The equipment's heterogeneous, the drivers are out of date, you're missing patches, you have conflicting hardware and software. We took 3 cards from 3 major manufacturers about 9 months ago. So we took 3 access points from the same major manufacturers, US Robotic, Netgear, and D-Link. Okay, that's a matrix of 3 cards that meet the Wi-Fi standards and have certified, and 3 routers that meet the Wi-Fi standards certified. That matrix, out of 9 entries, only 7 worked. There were 2 cards that wouldn't talk to 2 of the routers. And Yvonne helped us sort it out. There was an extra act they wanted on one of them that wasn't part of the standard. It's awful. And it's all on their websites. You can sort it out. Yvonne was able to sort it out. So you ought to be able to write a program to do that and accumulate his knowledge and make that work, right? And let him do something more constructive. The wireless ought to be the solution. The hardware and software is quirky, hard to install, much more complex than wireline network. The RF range and coverage issues are very important. I haven't found anybody, except maybe Paul Henry, who claims that a Wi-Fi system will cover their entire house. Okay, and the reason is because broadband comes in the corner of your house and the kids are in the diagonal corner in the basement. Right? And if you have a big enough house that you can afford all the networking and multiple computers, it doesn't make it. 50-foot range notwithstanding. There's nobody responsible for complete functioning. Users have to become experts in something they should have to know nothing about. And there's no accessible universal knowledge base of solutions. Okay, so what can we do about that? We have NIPs to burn in the network. In fact, it's a network of computers, which is sort of obvious. We ought to be able to use them to somehow simplify the tasks. The network design, installation, and maintenance ought to be automated. Learning algorithms that learn from experience and build up a repertoire of experience for classifying and analyzing network states. Collective successes and failures in a knowledge base. Partner and consult with human experts, leveraging the wizards, like Yvonne and others who know what they're doing, and get some kind of single point of responsibility solution. That turns out to be a very hard problem. It's an extremely hard problem, both from the point of view mathematically, I'll talk about that in a few minutes, from a computer science point of view, databases and everything, from human factors, and also economics. Who's going to pay for that kind of thing, and how can people really benefit from it? So it's an interesting problem. That's why DARPA was interested in it. That's why we got interested in it. It's got a lot of research content to it. And we have a lot of commercial companies. Every commercial company we've talked to says as soon as you have something that works halfway decently, we'll take it. Because there just isn't anything out there. Everybody's got their own solution for their own particular hardware. And we're starting some field trials right now in England. So I'll talk about that a little bit. Okay. If you want to solve this problem, what do you need? What does the solution have to look like from a high level? If you're just going to set up the general architecture, what do you need? First of all, you need to be able to talk between these nodes. Well, that's a bootstrap problem. How do you talk between nodes that don't have it when you don't have a network set up and nothing's quite working right? So that's the first problem. You have to be able to talk between things that don't talk to each other. And we have a way of doing that I want to talk a little bit about. It should only need a physical link of some kind. Has low overhead, and we call that the collaboration bus. The other thing you need are sensors on that bus. Sensors which will monitor what computers are doing, what routers are doing, what network traffic is doing, what kind of patches you need that you might not have. All these things are available. If you want to find out whether your router needs a new patch, that's available on the router website. But getting it is tough. Right? Getting it is tough. Did somebody say something back there? Okay. All right. You need state information for the nodes, operating system, the NIC firmware, registry, and so on. You also need traffic information, particularly for intrusion detection as well as for diagnosis. And all this has to be compressed through pattern analysis. Otherwise, all of your traffic on your network will be describing what the network is doing. And the network won't actually do anything. So there's a real problem there finding out what the important pieces of information are and keeping them. Then you need to have a machine intelligence, a cognitive system in the parlance. And the way we're doing this is with an algorithm called cost-sensitive fault remediation, which is just what it says. We want to fix problems. We want to measure how much each step of the troubleshooting costs, and then optimize that, which is what a good troubleshooter does. Well, you try this first. It's not likely to be broken, but it's real easy to fix. Or, if I got to reboot it, that's the last thing I'm going to try, if there are a lot of other easy things to try first. That's knowing the costs and going through and paying attention to them. It's based on reinforcement learning, which is a branch of machine learning that says you sort of continuously learn from experience, as people do. And reinforcement means just what it says. If you do it wrong, you give them a whack on the rear end, and if they do it right, you give them a lollipop, and you move on. You want to seed it with the best information you can get. You want to learn and update through experience. And that's what's really wrong now, because all the wizards for installing networks are hardwired in. So if you don't get a problem that you've already seen before, any place, you have to fix it by hand. And then once you fix it, somebody in Philadelphia who gets the same problem has to fix it all over again. There's no place to keep track of that until web pages get updated and so on. You really want to pool experience between the systems. And when the machine gives up, you want to call for and accept help from a remote expert. Right? And then finally, you need some kind of effector on the bus to fix it once you figure out what's wrong. And in fact, the fixing it is part of the diagnosis. I'm sure all of you have done troubleshooting where you try to fix something. If that doesn't work, it tells you something about what may be wrong. Right? That's all tied together. And there's a real issue here, and as usual, we always put it at the end. You need security at all the levels because you're really getting down into the guts of the system to make these kinds of changes and repairs. It's just as easy when you're doing heart surgery to damage somebody's heart as it is to fix it. Okay, so what does our bus look like? Let's take a look at this. I've got an example of a network here that's got a variety of different lengths. A wired link, a wireless link, a sneaker net link. You know a sneaker net? That's just, walking around with a floppy disk or a hard disk for those of you who are, or a CD or whatever. And a WAN tunnel out to a remote node. So what we have is a wired link here, and using the IP multicast channel, this PC can send important information out, such as, hello, I'm here, my parameters are, my IP, my net mask, and so on, my operating system. I see this traffic. What kind of traffic do I see over my part of the network? Here's what I know about other nodes that I've talked with, and I'd like you to make some measurements for me, please. Because there's some things I'm not sure about. Could you check in your part of the network and tell me something about that? Then this node down here picks it up and rebroadcasts not only the information that got in, but also his information from the green node, what he knows about the world. And what he picked up from the red node, he'll send on to blue here, who can then, blue will send back what he knows, and the guys down here with the sneaker net link can pass their information back and forth, which could be in the same room or another building if you need to, even if you don't have a physical link set up or can't get one set up. All the same protocol. And then finally this goes out to a remote node here, which is a virtual part of this network. You can do diagnostics and repair and has the database if you need it. What kind of features? You have a physical link. The information can be shared even before the network is working. All you need is an IP address of some kind, so you can talk on the multicast link. The sense and repair commands have to be transported even while it's in fault states and things aren't working right. It has to work with heterogeneous nodes. An XML message format is being used that allows hierarchical organization for the whole diagnostic thing. You can get to a remote node through an encrypted tunnel, and you can build up a collaborative picture of the network. It's not necessarily perfect, but you can build up a network, fill in the blanks, and the more you learn about the network, the more you can do to make the network bootstrapped up. Hidden nodes can be observed indirectly. You can look at patterns of traffic and states also. And this is important for intrusion and virus detection, which we've built in from the beginning to really be part of the overall function here. And very low overhead because you use feature maps of what's important. Okay, now I've got information on this network. I found a way to collect all my information. What am I going to do with it? I could just go through a scripted expert system and try to solve these problems and try to think of everything I can do. But I want to do better than that. I want it to keep getting better as it picks up experience, and that's one thing you can't do now. So the focus is really to improve the performance on this one thing, the fault repair task. And I want to minimize the cost, which is generally elapsed time, but the cost could be other things. For example, it might be cheaper for you to go get a cup of coffee and do something else and just reboot the thing than to sit there and try 4 things that each take 30 seconds apiece. You have to sit there and wait. So you have to decide what the cost is. But you can decide, you can measure the cost for repairing the fault. You know the cost of a diagnostic measurement. You know the cost of a attempted repair action. And this is an important point, because this is something you can't put in an expert system. You can learn the statistics of the fault states. That means if it usually breaks this way, these are the set of things you try first. Now, Ivan knows that by heart, right, for this particular network. But if you went over a network in core, it might not be the same thing. Right? And that's something you need to learn, and that makes an enormous difference on how you handle repairing faults. We actually did this with some disk drive fault data and found that it actually saved time. The human expert had a particular troubleshooting regimen, but if you look at the statistics, it was better to replace the disk much earlier than they were usually doing in terms of cost, because the other things were just not likely enough to be fixed until you got very far down the list and you would have wasted a lot of time. You want the measurements to be continuous, and here's the mathematics and computer science part. The measurements are going to be wrong. They're going to be incomplete. They're going to be noisy. They're going to conflict. They're not going to give you good results. But even with those incorrect results, you want to get the best troubleshooting you can. A good example, and I don't have any here, we were over in the Hill building. I was using LAN, which is the network that's working over in the Hill building. And I lost my internet. Boom, didn't work anymore. Couldn't get email off my internet. And so I popped up this software, and it went through and said, you don't have a valid IP address anymore. You've lost your lease. And it fiddled around for a while, and it gave me my lease back. Then I lost it again, and it gave me the lease back immediately because it knew that was what had fixed it before. Even though the first time I hadn't lost my net mask when I lost my IP address, because there's a time constant for these things. When you lose your lease, some things fail before other things break. So you take a snapshot picture, and it won't look the same as a snapshot for an identical fault at a different part of the cycle later on. You have to sort of cluster these things together. It's an interesting learning problem if you've looked at learning algorithms. You want to learn from your successes and failures, and you want to make the best use of expert input when you need to. So when you call Ivan in Omaha, and he fixes it over this tunnel, that's the last time you have to call him, because that gets propagated around, and it becomes a known solution to that problem. It sounds rather trivial, but it actually is very important because we're not doing it now.
Excuse me, Rich.
Yes.
There is an important complications here. It's a problem identification. How exactly you make sure that 2 problems, one which is solved, the other is to be solved, are really the same one?
I'll show you.
Because the space has so many parameters, that's actually this simple thing can become really...
That's the interesting part about the machine learning, is how do you go through, collect enough examples. And one of the things we want to do is come into some unsuspecting operation, like say WINLAB, set up the software and collect all the faults on the network and start building up a lexicon of faults, right? Because this is a nice piece of software. It's just like a newborn baby. It's stupid when you start it. It's only whatever you think of. But the more experience it picks up, it quickly gets better. And we found out that 90% of the problems can be solved by renewing your IP lease rather than rebooting already. So this is an interesting result. We need new varieties of reinforcement learning if you're a machine learning person. So this is getting into new territory now. What can we do? Just to give you some definitions. The underlying faults in the system, we're calling states, network states of particular fault states. We want to observe the state attributes, and that costs something. And we want to remediate the fault states, and that also costs something. That'll repair some states and fail on others. Okay, it's a really hard problem, as you were suggesting. So we're starting out with a simplification. Fault remediation episodes are independent. We're assuming only one thing's broken. Okay, that's not always true, but it's a good starting place. We want to use high-level actions. We'll either provide information or repair things, not break them further, which is also a simplification. Otherwise, there are no fault mode changes, and we want the minimum cost of repair. Okay. What we're doing here, I'll just talk about this one because I'm going to show a movie of this here. We have no state changes as we go through. The repair is all or nothing. It either fixes it or doesn't make it worse. And we continue this episode. We keep trying until we get the thing fixed. Okay, what do I mean by observables? Okay, here's an example. Action 1. Is the network medium physically connected? That's something you can measure with a sensor on the network. Is the active interface wireless? Is the active interface DHCP enabled? Can I ping my IP? Can I ping localhost? Can I ping a gateway? Can I do a DNS lookup? Can I reach an external website? Can the external website get a DNS server? Right? Which means it may not be me, it may be the DNS server that's down. Is the DHCP DNS setting valid? Can an external website reach Yahoo or someplace else that's known to be up a lot of the time? So these things are all, you can imagine why these are useful diagnostics tools, the kind of thing you would do if you could. Check on another machine, is another machine getting to Yahoo? All these things, you add them up. So we can make these. Now each one of these has a cost. Renewing the lease has a cost of success. These are in arbitrary units. That's pretty small if it's successful. If it's not successful, you sit there hung for a while before it times down and gives up. So that costs you something. And it repairs a certain number of faults. Plug your network cable back in. Well, if you're successful, it's okay. If you're not successful, you've already moved the computer out from the wall and you're really ticked off and you kick it and it's got a high cost to you. Check your router's physical connection to the ISP. Contact the ISP and report their DNS server appears to be down. Well, if you're successful, that's fine. If you're unsuccessful, then hang around on the Audix machine for an hour and a half trying to get somebody to answer the phone. The cost to you is probably quite high because it doesn't fix the problem and you're really ticked off at that point. So you put cost values on the bidder here. And what we found is this is a huge improvement experimentally over classification. Classification means you just measure everything and you try to figure out what the fault was. It's much better to go through and try something and try something else and try something else until you get to the end. It's a lot cheaper. And how do we know if the fault succeeds? And that's an interesting problem in machine learning. We go back and check the primary complaint, or we build monitors into the software. Let me give you an example of what we're really talking about here. I've got a little movie which shows all the pieces, and Microsoft is protecting me from myself here. Okay. And this is in a verbose mode, so you're going to see all the guts of the program working on here. It sets up the program, which is all in Java, and let me get down here to my little bloody thing. Okay. Got to have your copyrights, you know who to blame. And play. Actually, I can go forward here. Okay. And I'm looking for, I send out a hello packet. And I see what's going on. Everything's happy. And I'm going to come back. I'm going to do a test. This is a break your network button over here. I'm going to kill my DHCP lease and see what happens. Okay, the system's determined there may be a problem. Click OK to self-repair. So I click on it. Okay, what happens? I keep trying. I can't get to the NIC. Maybe the NIC's disconnected. So it tries a bunch of things. The NIC's disconnected. Datagram didn't work. It tried to renew the lease. It got a repair. Okay, and this computer didn't know anything. So it's now said, okay, I tried this. The medium is connected, DHCP enabled. I can't ping my IP. I can't ping localhost. I can't ping gateway. It ran through this whole set of things. It tried renewing the lease, and that worked. Okay, now we're going to do it again. It had no idea what to do to repair this problem. It had never seen it before. It's showing you there's a newly recognized state. This is what you were talking about. There's a state of the network. And the state has some value, and here's the value. The episode, this set of things I went through, and here are the measurements I made, here's what they cost, and here was the result. Now I'm going to do it again. I'm going to break it again and see what happens. I kill my DHCP lease. I've got a problem. And, okay, it fails, and it immediately fixes it. Okay, it says, oh, the last time I finally fixed it when I got the renewed DHCP lease. The first measurement I said looked pretty good. It came close. It said, okay, here's a new episode. I observed a new episode. It's a different one, right? I can ping localhost. And the medium's connected, but the IP is not valid, but the net mask is valid. It's a different, slightly state. But it immediately renewed the DHCP lease because it was close enough to the last one. I'm going to put them both up here. And let's see if I can do this and make it stop. Pause here. Oops. Go back one. So you can see them both. Look. See where they are? Yep. Back, spot. Okay. See? Success, failure. Success, failure. A success, a failure, a success here. And here the gateway looked wrong. Here the gateway looked good. But these failed already. It says, well, you know, the first 5 looked the same as the last episode. Let's try to fix the DHCP lease. Maybe that'll work. Tried it, immediately fixed it. And the cost, look at the difference in the cost. The cost here was 1,111,500. The cost here was 1. Then I started doing a bunch of expensive stuff. I avoided all the expensive cuts because this one worked the last time I tried something. Let's get rid of the expensive stuff. And so the whole process was much more efficient. Okay, let me get out of this. Hello. How do I get out of pause? How about pushing on the right mouse click? Okay. Get out of that. Okay. That's how the learning works. Where are we now? We're looking at optimal if we're doing optimal results on few faults. And the algorithm is deterministic and it's optimal. It gives you the best diagnosis with the known statistics. The more faults you get, the better your statistics, the better you can do it. We need to explore this better. We need to scale it. There are a lot of interesting scaling problems to get rid of the combinatorial explosion. And you want to handle continuous noisy experiments and deal with side effects. Where are we going to go from here? And this is the big issue in machine learning that DARPA is very interested. How do we get this into handling large problems? Well, we can either lump things together into large states, into boxes. We know how to do that, but it's hard to determine what resolution to use. You can curve fit it, do parameterization for the learning. That's used a lot. Neural networks use that. But the problem is it's very hard to tune it right and make it work. So I think what we're going to try first is to say memory is dirt cheap and just record everything. Record everything that ever fails. Keep track of all the errors. And you can get a good match for continuous observation. Nobody's really done this before. But we think we can do that, and in some sense, that's what Google does. It goes through and just keeps huge, large databases with indices to them. And Michael used to be involved with Google, so it's an interesting way to do it. I want to talk about this. Where are we going from here? We're going to take the collaboration bus more fully into decision making. And one of the things we can do is get multiple perspectives of the network. This node sees the network this way, like the old parable about the blind man and the elephant. Has everyone seen that parable, right? Everyone gets a different view of the network depending on where they are. We want to take advantage of that and use cooperation. And we want to use the bus as an active agent for synthesizing this global perspective, particularly from isolated nodes. And understand more about the context, which is a very hard machine learning problem. The machine should know what it's doing and why. And understanding what no means and what why means is a big issue right now in the machine learning community. And the sort of classical thing what you'd use it for. Now right now, this ought to be of interest to the guys here in WINLAB. As you know, hotspots are growing fast. Hotspots are not quite info stations in the sense that you're not necessarily going to dump a lot of data down, but it's you walk into a place and you've got internet connectivity. They're very fast-growing applications. McDonald's, Starbucks, they're very interested in Europe. It's a great first application because we can exercise the collaboration bus, get data from a real system, and get some commercial value before we really have the learning part working. What do the providers want out of it? They want configuration, easy configuration for multiple nodes, security and liability. Liability is an interesting problem. I mean, there's scenarios where you can go out and buy a network card, go into a hotspot, hack into somebody's website, and then throw the NIC card into the river, and that's the end of that. And you would like to be able to cache traffic over a hotspot and be able to pull it out if it's subpoenaed. There are real issues involved with that, particularly after 9/11. Users out of this want configuration assistance. Imagine this. I have a workshop full of high-quality geeks. I mean, the very best. About 25 or 30 of them in a room with SF-LAN, this wireless hotspot in San Francisco, coming in through the window. Half of them couldn't get their laptops connected to SF-LAN in a rational amount of time, where that was sort of the first half day. It just, there was something wrong here or something wrong there, or it was just ridiculous. Users would really like to be able to handle configuration, file sharing, privacy protection, and so on. So what we do, imagine you've got a Wi-Fi hotspot here. We have one computer on the hotspot, which is a monitor, and a gateway through a VPN tunnel off to our remote site. They can sit there and monitor all these things, keep track of what's going on, as well as under company hotspots, keep track of security alerts, usage trends, and get browser-based reports out of all of this. We're doing this in England right now with a company that's setting up hotspots and libraries all over England. That's going to give us a real handle into some of this hardware and what goes wrong in hotspots. People don't have any idea how well they work yet. Because right now, about 3% of the people that go into Starbucks use the hotspots. And those are the road warriors, or the windshield warriors, as they call them, windshield wiper warriors, as they call them sometimes. The guys that really know what they're doing. The average person doesn't go in and use the hotspot or even know that it's there or what to do with it. And clearly they want a much bigger draw than just 3% of the customer base. We want to know things about network traffic, user demographics, kind of activity people are going to be using, how to optimize your network to handle that. Bandwidth use is very important. If people are going to be downloading a lot of videos, you may really want to configure your network differently or have limited access, session links, usage by location, recurring usage, security issues, and inward security for businesses and customers, outward security for liability. You want to protect the users inside the network, do security scans, inter-packet analysis for real-time logging, and there's a lot of interest in England, at least, in third-party escrows. So you can log the traffic by machine, escrow it automatically, nobody looks at the traffic, and it stays there until a subpoena pulls it out. And for the whole set of traffic here. Now, I'm going to see whether the internet's actually working here. This will be amusing. Oh, look at that. This might actually work. Okay, and this is partisan traffic we did a couple of weeks ago. Just give you a sense of today at a glance. This is what's happening on the hotspot. We have web traffic, email traffic, instant messaging, and so on. And this is, we haven't used it in about 2 weeks, so there's no traffic today. But if I go back and I pick one up, say web traffic, I can get it daily, weekly, monthly. I'll go back a couple of weeks. And you see we had traffic here, packets, statistics for the packets, and I can get the raw data back out. What the packets are, who they are, where they went to, and so on. And where the connections went, what kind of email connections, instant messaging. I don't think we had any instant messaging traffic. This is monthly, no we didn't. But there was some security warnings. Let's see, monthly. No, and past where we had security warnings, email. Anybody have email in here? Yeah, okay, here's some email. Here's the web traffic for email. Connect to the outside and so on. So this is up and running now. It's kind of an interesting way we can get some ideas on how this works, what people do on real hotspots, what real people do on real hotspots. And from a machine learning point of view, this is incredibly important. And I can't, if you ever get involved in machine learning, I have one thing to pontificate about: get real data. I used to work in handwriting recognition a long time ago. And what you found out was all the people in handwriting recognition had their secretaries or their grad students write down all the digits from 0 to 9, and they would try to read them. Garbage. Just didn't work. I mean, it always worked, but it didn't teach you anything, because it wouldn't work on the other next grad student coming down. We went to St. Louis, Missouri, the middle of the country, went to a post office scanner with real letters coming through and read the zip codes off the letters. Got tens of thousands of zip code digits off of real letters with coffee stains and cross-outs and blots of ink and upside down and dyslexic people and everything else. That data was great. Because that data, you could actually learn something with the real statistics in it about how the world really works. And so that's what we're going to try to do here and see whether we can get some of that statistics out for the real world. And I think Ivan has volunteered to put this online here, right?
I did.
Right, Ivan? Okay. And try to get some statistics off and see what this particular ethnographically diverse group of computer users do here. Although I'd really rather to get the network in the English department, which would be more representative of the real world or something like that. But we'll see what happens.
We would probably get more abuse here than we do.
Well, but it's a different kind of abuse. It's sort of intentional abuse, hacking, people that know half what they need to know to make it work. And they get in and hack a little at something, trying to fix it, and then break it royally. People that are really scared of it and have no idea what's going on break it in different ways. So anyway, that's where we are now, and we'll keep you guys up to date. And people want to play with this. I know Ray had a student that was interested in that. Anyone wants to play with this bus? It's all in Java. It's all open source, and we can get in there and do that. And it's an interesting way of connecting computers together. Yes.
One of your first problems that you mentioned was about cards not following standards or providing something outside the standard.
Sure. Once I get Ivan to get me the drivers for Windows, so I can get into the cards, you can fix that stuff. You know what card it is, you know the firmware, you know the chip rev, you know everything you need to know about it, you can read out. So you know what's wrong, what's broken. You only have to figure that out once. We figured it out once here for that particular, what was it, a US Robotics and a D-Link card, D-Link router, I guess.
But how does the program come to the conclusion?
It may not be able to figure it out the first time, but the second time it'll figure it out that in your particular setup that's going on. So since there are only 9 entries in the table, right. And if it's on their website, you'll be able to include that into your, just be sure you have the latest rev of the firmware. I mean, a lot of these problems are just getting the latest rev of the firmware and the operating system patches, which those can all be automatic.
And second question, a little tangential, but you said on hotspots you want accountability from people who use the hotspot. How do you figure out who's using the hotspot? The whole point is
you want to at least be able to track backwards whether the problem came out of that hotspot.
Up to that point you can, but beyond that point...
Beyond that point, you may not be able to. But there are real issues for knowing whether the traffic is coming from that and whether you can get a court order that says, you know, somebody's running around the city doing X, Y, or Z. I want these hotspots to monitor for that kind of traffic. And since you're monitoring on us in a stateful way, packet by packet, you can look for patterns. Right? And in particular, the security software that's built into this is a pattern software. It's written by a guy that used to write security software for things like Carnivore. And so he knows how to do pattern matching and look for new patterns that are interesting.
And also, you at least have the MAC address of his NIC card. Even if he throws it into the river, but somebody fishes it back, and then they will want to track all the movements of this guy within the city by his MAC address.
None of these things are perfect, and there's a different trade-off in England than there is in the United States around privacy and national security issues. Right? And so different legal systems handle that differently. And that's important to know if you're setting up standards.
Actually, in England, with their proliferation of video cameras, you might have an interesting correlation. If one of the parameters, by analyzing the traffic, you can know from which direction it comes. You actually might try to tell this camera to simultaneously analyze the data log and the log from a certain video camera and correlate them, and actually you might see the guy.
I'm not sure what the numbers are in the U.S., but there are an awful lot of those cameras in the U.S. already.
I know.
Enormous
You don't know about that.
The territory is so large.
You just don't know about them.
No, the territory is so large that uniformly placing cameras in both countries, like here, it requires much more cameras.
Yes. My favorite camera is on the backside of Snowbird. I can sit there and watch people coming down the runs in the wintertime and decide whether the snow's any good. I don't have to depend upon their weather reports. Okay, yes.
You had talked about self-repairing networks.
Yes.
And each problem has a set of parameters.
Yes.
So isn't it possible that two different problems have the same set of parameters? And with that set of parameters, you have mapped it to a certain repair process.
And if it doesn't work,
yes.
Absolutely. What that means is you need a new sensor.
It's
Because-
possible that you can have one-to-many mapping, right? As in the same set of parameters.
That says you don't have enough sensors.
Right.
Right. And so that's an evolutionary issue. If you see the pattern that there are errors which get fixed the same error gets fixed different ways at different times, that's a flag going up saying you better evolve a new sensor.
So you have to change the whole set of parameters itself. Or add
No, you just add a sensor. This is all XML. You just add another XML tag for a new sensor. You have to write the sensor. The sensor has to do something like, look for a particular bit pattern in a packet or do something else. So you have to write a sensor. Insert the sensor into the software in a modular way, and then that gets added to the group of things, and then it will start tracking these and see that the degeneracy gets broken. Right, the one-to-many mapping gets broken, and here's one bin and here's another. And then if that happens often enough, the learning system will try that sensor first, right, before trying all the others, which it knows are going to be likely to be one-to-many and not give you new information. It'll maximize the entropy for each measurement. That's a good point. That's evolution, not learning. Okay. Yes?
In your image example, the process got triggered by your attempt to do something that didn't work, right?
In the movie, you mean?
Yeah.
Yes.
Would that imply that it would not know that there was a problem, even though the problem is already there? It would not know there's a problem?
Oh, it knew there was a problem. It was asking me, it was telling me in a verbose way, I think there's a problem, give me credit for solving it by clicking on OK.
Sure, but it didn't do that until you asked it to do something that triggered that problem to be recognized.
No, if I had it in a quiet mode, it would have just gone through the whole process you saw. Right? It was asking my permission to continue. It wasn't asking me whether...
It would have found the problem if you...
It would have found the problem, exactly. But for the purposes, for pedagogical purposes, I had it say everything that it was doing.
What about problems that imply a deterioration of performance, not an outage? Does it work for that?
It will do that because that's why you keep track of traffic and ping times and things. And one of the sensors you write is ping time. I mean, all those aren't implemented, but that's exactly how you would handle it. One of the things we're really worried about is performance. And you would do a ping time, or a time to retrieve a file of known size from our website, right? And so if that gets to be too long, you know there's a deterioration. Now, one of the things that bothers me about email and web traffic, you know, at a very deep level, I have no idea how well it works. Right? Nobody knows how well it works. If I send a letter from New Jersey to Omaha, Nebraska, I can give you the statistics for what fraction of letters get through in 1 day, what fraction of letters get through in 2 days, and what fraction of letters never make it through. I can give you 2 decimal digits on statistical accuracy of New Jersey to Omaha, Nebraska. But I have no idea for email what fraction of my email to an address in Walla Walla, Washington gets through in 1 minute, 5 minutes, 10 minutes, or never. I have no idea. Nobody has any idea. Nobody knows. It would make a whole lot of sense to collect some of that data if you're using that, if that's contributing to a 3% or 2% of the GDP growth in this country. It would be kind of nice to know something about it. From sort of a larger policy point of view, we know nothing. And you would like, that's one of the things you can monitor. And it would be very interesting to do. Anybody else? Okay, good.
Thank you.